In chemistry, the study of energy changes in reactions is essential to understanding how and why these processes occur. Exothermic and endothermic reactions are two fundamental types of reactions that involve the transfer of energy, and this transfer can be measured to provide insights into the reaction dynamics. Additionally, reaction profiles, also known as energy diagrams, visually represent these energy changes, offering a clearer picture of the processes involved. To begin with, energy transfer in chemical reactions can be measured using calorimetry. Calorimetry involves capturing the heat exchanged between a chemical system and its surroundings during a reaction. By using a calorimeter, a device designed to measure heat changes, scientists can determine the amount of energy released or absorbed in a reaction. This measurement is crucial because it quantifies the energy change, allowing us to classify the reaction as either exothermic or endothermic. In an exothermic reaction, the measured energy transfer will show a release of heat, indicating that the system has lost energy to its surroundings. For instance, when a fuel like propane combusts, the energy released from forming carbon dioxide and water is greater than the energy needed to break the bonds in propane and oxygen molecules. This results in a net release of energy, which is why a combustion reaction feels hot and can be used to generate heat for practical purposes like heating homes or powering engines. Conversely, in an endothermic reaction, calorimetry will reveal that the system absorbs energy from the surroundings, which is reflected in a decrease in temperature. A classic example is the dissolution of ammonium nitrate in water, where the salt absorbs heat to break apart its ions, resulting in a cooling effect that can be measured. This absorption of energy indicates that the bonds in the reactants required more energy to break than was released by forming new bonds in the products. Reaction profiles, or energy diagrams, are graphical representations that show the energy changes during a chemical reaction. These profiles illustrate the relative energy levels of the reactants and products, as well as the activation energy, which is the minimum energy required to initiate the reaction. The y-axis of a reaction profile typically represents the energy level, while the x-axis represents the progress of the reaction from reactants to products. In an exothermic reaction profile, the energy level of the reactants is higher than that of the products. The diagram shows a downward slope from reactants to products, indicating that energy is released as the reaction proceeds. The peak of the curve represents the activation energy, which must be overcome for the reaction to occur. Once the activation energy is surpassed, the reaction releases energy, resulting in products at a lower energy state. In contrast, an endothermic reaction profile shows that the energy level of the reactants is lower than that of the products. The diagram features an upward slope, indicating that energy must be absorbed for the reaction to progress. The activation energy in this case is also a barrier that must be overcome. But since the products are at a higher energy level than the reactants, the reaction absorbs energy, which is depicted by the products being at a higher point on the energy scale than the reactants. These reaction profiles are essential for understanding the energy dynamics of chemical reactions. They provide a visual representation of how much energy is needed to start a reaction activation energy, and whether the overall process will result in a net release or absorption of energy. This information is crucial for predicting the behavior of reactions under different conditions, and for designing processes that either harness the energy released by exothermic reactions or provide the necessary energy input for endothermic ones. In summary, energy transfer in chemical reactions can be measured using calorimetry, allowing scientists to quantify the heat released or absorbed during a reaction. Reaction profiles then provide a visual representation of these energy changes, showing the relative energy levels of reactants and products, and the activation energy required for the reaction to proceed. These tools together offer a comprehensive understanding of the energy dynamics that drive chemical reactions.